Okay, so this is a half reaction for the spring 2017, and I'm going to solve this. So the way that the problem is written is the following reaction happening in KOH. And as you can see in all the aqueous sign, that means KOH and water the allowed quantities that you guys can write it here. Okay, so I will need to do the half reaction. So I'm going to do the first half reaction, which is a C3H8O2. Okay, and then C3H8O2. So then what do I write on the other side is C3H2O4K2. Okay, so that's what I wrote, and then I need to essentially finish that up to solve that problems. Okay, so where do I have my? Oh yeah, here it is. Okay, I lost my notes. Okay. And then what do I do is, okay, and then I am going to looking at the carbon is okay. Let's look at the K2. So, okay, here is I'm allowed to write a K2, so let me say KOH, because KOH is a known quantity that I can use. And then I need 2, so I need a 2 KOH, okay? And okay, so once I finish the KOH, then I am going to see how many oxygens do I have. Oxygen is, you have oxygen is, how many oxygens you have? You have 4 oxygens, right? How many oxygen do you have? You have 4 oxygens. And then this one is you have 4 oxygens. So the oxygen rise, I'm okay. So what about the number of hydrogens now? So let me delete that. Oxygen is I don't have to worry about. And then hydrogen. Okay, as far as the hydrogen is concerned, I have 10 hydrogens. And how many hydrogens do you have? You have 2 hydrogens. So therefore, what you need to do now is, okay, I need to compensate that by adding 8 hydrogens, right? And that hydrogen, you cannot really do it, so I have to put it in H+. So this is regardless, remember the acid-base reaction, regardless is acidic or basic condition, the rule of thumb is start with an acidic, and then you guys can change it to the OH later on if you need it, right? So for now, I took the convenience of balancing oxygen using water and balancing the hydrogen using H+. And then finally, I can do the 8 electron to balance the charges. So I have done the first big task about balancing the first equation. Okay, and let me do the second equation, which is KMnO4 and MnO2. Okay, here we go. So this one is also, once again, the potassium. I can use KOH because that's the one that is allowed. So K is written on the right hand side, and the mangan is there. Good. K is there. Now, 4 water, 4 oxygen, 3 oxygen. So you need an H2O here. And then what else do you need? Okay, so far I have balanced all this potassium, mangan, and then I have balanced the oxygens. So now let's pay attention to the number of hydrogens, which is 3, and I have none. So therefore, I need to add 3 hydrogens here. and then I need to add 3 electrons to compensate those charges, right? So, okay, so I have done so far so good. Okay, so these are all the balanced reaction, and then what I need to do next is I want to essentially get rid of this electron. So the way that I do is you multiply by 3, and this reaction is multiplied by 8, and you're going to add them up. Okay, so this similar exercise has been done in the Chem 1, but this is a little bit more elaborate version on this. So which one is, though I love to get rid of the electrons, and then I start to write it as a 3 times C3H8O2, okay, and then this is a 6 KOH, and then this is a 8 KMnO4 plus 24. Okay, it's actually, if you realize, this is also gone as well, so I don't have to worry about it. So actually that's also very convenient because they kind of cancel out each other. I don't need to worry about it. And then this one goes away, and then same thing, 3 times C3H2O4K2 plus 8 times MnO2 plus 8 times KOH plus 8 times H2O. Okay, and then you will see that KOH is gone. I can make it this as a 2. So this is a complete reaction, and they want to see that C3H4O2. So that's the one. You will see the 3 and KMnO4, which is a KMnO4. Where is it now? Yeah, here, you need an A. So that's an A is an answer for this. So this is a pretty elaborate one. Knowing your constraint, once again, this is a reaction in KOH and in an aqueous solution. So aqueous solution means water can be used. And I also use H plus and an electrons to sort of balancing all the oxygens and the hydrogens and the electrons. And finally, just like we do normally in the half reaction, we can write that equation that way, so that to delete the electrons. Okay. Okay, so let me solve this second problem. Sorry about this. And this one is, let me read this problem with you guys. Reading the problem is actually quite important, so I wanted to do it. So this is a galvanic cell, means you kind of the reduction and the oxidation going on, and the copper becomes copper 2 plus, and the cadmium becomes a cadmium 2 plus. And which one following the standard notation of the cell? And then what you need to do is, I discussed this one before, the electrochemical reduction potential. You go and look at it, copper 2 plus 2 electron, this reduction, and is E naught, which is a reduction value, was 0.340. Okay, and the cadmium 2 plus with 2 electrons is cadmium 0, and that's a minus 0.40. So then what did I tell you about which one is a winner? This is a winner, right? So let's write winner. This one wins. Okay, so this one wins. So let's say wins. So what that means is you're going to keep the reduction as it is, and this is a loser, which is going the other way. Oxidation is going to happen, and then so therefore we want to keep it as way, and this is a reduction. The oxidation that's spontaneously going to happen is cadmium will be oxidized into cadmium 2 plus and 2 electrons, and then if you add them together, this 2 electron goes away, so it is a net reaction will be copper 2 plus, cadmium cadmium 0, the copper metal, and the cadmium 2 plus. So that, and then actually the E cell not will be a 0.34 plus 0.40. Okay, so because of the reverse, the reduction potential should be reversed for the oxidation potential, and you just add them up. So, and then this half cell notation is, in a very simple way, you want to write an anode, salt bridge, and cathode. This is a very simplified form. There are more complicated ways to saying this. So that's what's happening. And then there is a little trick that people talk about, the anode and cathode. And anode is ox, and cathode is red cat. Okay, so these are you have to think about the ox versus a cat, and the cat is always red. So what that means is here we are talking about something that oxidation. This is an oxidation. The cathode is a reduction, right? Red cat. So which one is doing the oxidation? The cathode, no, the cadmium. I'm sorry, this is supposed to CD. So that's an oxidation. That's an oxidation. So that's good to see, and this cannot be actually written in that way. And then what's the reduction is? Reduction is from here to there, right? So that's a reduction happening this way. So therefore, the D is the answer. So remember, the half cell reaction is written in this way. Okay. So far, so good. There are other versions, and I can continue to, you guys should continue to look for the answers in the YouTube and so on. Okay, so let's look at this. This problem is actually pretty simple to do, but there is something interesting to remember. So which one? They show you this to reduction. So this is all reduction. That's good. And which one is a bigger one? Okay, so this is a larger value, compare that. So this is a winner, right? This one wins. So therefore, we'll keep this one as it is, and we'll make this one oxidation on the other way, right? And that's what is going to happen. And so if you see that actually bromine is reduced, so that's a reduction, and the lead is being oxidized. So this is a good way to spontaneous reaction. And I can write it in here clearly. E cell, there are different notation, but I like to write it this way. Reduction plus E oxidation. Okay? And the reduction is the one you see here, which is a plus 1.07. And plus, oxidation is essentially opposite of this value. Okay, so what I mean is standard potential of oxidation is a negative of the reduction value, and then here, therefore it will be a plus, because opposite of the opposite, 0.13. So therefore 1.20 volts, and that will be your standard electrochemical standard cell potential, right? So that's what that means is E naught cell. Okay. I can solve the one more problem, and this is also worth for you to know. So let me talk about this. This is actually delta G. So what do I do with this delta G reaction for the balanced reaction? If you guys can go to look at your reference sheet, there is an equation that really related to this one. Delta G is minus NFE. So as long as you can find this one out, we can start to figure this one out. So what I just showed to you was like this. Delta G was minus NFE. E. Actually, it was like that. And then for we can apply that for same thing for standard condition. We can apply this as well. So we need to figure out what will be the N and what will be the E naught. And the one thing is you need to N is you need to from write on half reactions. Okay, we need the number of electron that is being transferred from redox reaction. And the E naught is, remember, this is very important. It is an extensive properties. Okay, not extensive. I'm sorry. No, it's not extensive. I'm trying to emphasize it's not extensive. It's actually intensive property. Okay, and this makes your actual calculation extremely easy for doing this. So because of that, I need to write this equation down into the form of a half reaction, and then if you write it down, okay. So let me start from the scratch, right? So aluminum solid, aluminum 3 plus with a 3 electrons, right? And then the magnesium 2 plus, and then Mg naught, right? This is a metal. So okay, I cannot write that way. Mg. And then plus 2 electrons. So I can write this way. And then what do I do is to complete the half-cell reactions, I need to multiply this one by 2. I need to multiply this one by 3. And so therefore you will ended up getting 2Al0, 3Mg2 plus 6 electrons, 2Al3 plus Mg naught 3 times plus 6 electrons. Normally I don't write the equation this way, but this time I want to emphasize this, which is going to be canceled out. But from this reaction, you know now N is 6. The 6 electrons is involved in the transaction. So I know this one is a 6 now. And then I need to know my E potential. So what do I do is I'm going to look at the values, and the magnesium is the reduction potential, right? So I can copy down the reduction potential, which is a E naught, is minus 2.37. And then this one is actually oxidation. You see this here? So I can find the reduction value, which is a minus 1.66, but I need to put a negative value on that because this is a reduction and this is an oxidation value. But I need, as the reaction is being defined in this way, therefore E cell not. So this is a E cell for this combined equation, and you will see that minus 0.71 volts. This one already gives you an important clue. This reaction has a negative potential, means this is not spontaneous. Spontaneous. Okay. Oh, I'm sorry. That spontaneous. And so what that means is delta G naught value will going to be positive, and this is already, I anticipate that. So from these choices, this is already a not good answer. Among 3 of them will be my choice. And then all I need to do is now to solve this one to saying, okay, delta G naught, which is minus 6. F is 96500. That's a coulomb per mole electrons. This is actually more electrons, right? And multiply by E cell, which is a minus 0.71. And if you do the math, you will get 4.1 10 to the 2 kilojoule with a plus sign. Okay, so that's the answer for this. Okay, so I come a long way. This is when I stopped due to the difficulties. I had an issue. I'm sorry about the trouble that we had to